All right, let's talk about lifetimes in Rust. If you've ever tried building something serious, say a program for Solana, you've definitely run into them. Now, lifetimes are, without a doubt, one of Rust's most powerful features for making sure your code is safe. But let's be real, they can also be one of the most confusing. So today, we're going to pull back the curtain and really figure them out.
Just so you know, this explainer was put together by us here at Forge College. Our whole goal today is to get you comfortable with understanding, debugging, and yeah, maybe even mastering Rust lifetimes. So let's just dive right in.
Okay, so before we can even talk about lifetimes, you've got to meet their enforcer, the borrow checker. I love this analogy. Think of it like a grumpy old but super well-meaning guardian. It seems incredibly strict, right? But its one and only job is to stop you from making those nasty memory mistakes that could just blow up your program.
And look, if you've ever felt like you're just constantly fighting with this guardian, you are so not alone. Honestly, it's pretty much a rite of passage for every single person learning Rust to feel like they're in a shouting match with their own compiler.
Yeah, does this look familiar? This classic error, borrowed value does not live long enough. This is basically that grumpy guardian slamming the door and yelling, "Nope, not on my watch." It looks super scary, I know. But I promise, by the time we're done here, you're going to know exactly what it means and even better, how to fix it.
So here's the big mindset shift. Lifetimes aren't just some annoying hurdle the compiler throws at you. No, they're actually the language we use to talk to the borrow checker. It's how we explain what we're trying to do and prove to that grumpy guardian that our code is totally safe.
So, what is a lifetime really? Well, at its core, it's just a way for the compiler to double-check that any reference you're using, any pointer to some data, will always point to something that actually exists. It's a guarantee you get before your code even runs, and it wipes out an entire category of nasty bugs.
Okay, so this is the happy path. This is what we want. We've got our data inside this solid box, living happily inside its little scope. And our reference, that arrow, is pointing right at it. As long as the data is alive, the reference is valid. Simple, right? The reference doesn't outlive the thing it's pointing to. This is what makes our guardian smile. Well, maybe not smile, but at least not yell at us.
But this is the nightmare scenario. This is exactly what the borrow checker is there to stop. See how the box, our data, has just crumbled away? Its scope ended. But our arrow, our reference, is still pointing to, well, to nothing. It's pointing to dust. That's a dangling reference, and it's the source of so many crashes and security holes in other languages. Rust's lifetimes make sure this can never happen.
Okay, theory is cool and all, but let's get our hands dirty. We're going to walk through and solve 3 super common lifetime puzzles. You can think of this as learning the guardian's top 3 complaints so you can get ahead of them.
Puzzle number 1 is an absolute classic. I like to call it the local escape artist. This is when a function creates some data all on its own, and then tries to let a reference to it escape out into the world. Spoiler alert, its escape plan is doomed.
So check this out. On the left, we've got the buggy code. The function creates a new vector of words inside itself, and then it tries to return a reference to just the first word. But here's the problem. That vector, it only exists inside the function. The moment that function is done, poof, the vector is gone. The reference will be pointing at garbage, so the borrow checker slams the brakes. Now look at the right. The fix is actually pretty elegant. Instead of making new data, we just borrow a slice directly from the original string that was passed in. Since we know that original string will still be around after our function finishes, the reference is perfectly safe.
And this is how we tell the compiler what we're doing. See that little ticker thing? That's a lifetime annotation. It's us making a promise. We're basically telling the compiler, hey, just so you know, the reference I'm handing back will live for at least as long as the input string you gave me. The borrow checker sees that we've connected the input's life to the output's life, it understands our promise, and it lets us pass.
All right, puzzle number 2, the overeager closure. This one happens with closures, those little anonymous functions. The problem is when a closure tries to just borrow some data from where it was created, but that closure is meant to be used later, long after that data is gone.
So what's the deal here? On the left, our closure is just borrowing a variable from its surroundings, but we're trying to return the closure so it can be used somewhere else later on. By then, that original variable will be ancient history, which means we'd have another dangling reference. The fix, on the right, is so simple but so powerful, the move keyword. This tells the closure, hey, don't just borrow that data, take it with you. It forces the closure to take full ownership. It's like the closure is packing its own lunchbox, so it has everything it needs to survive, no matter where it goes.
So here's the rule of thumb. If your closure needs to live longer than the function it was born in, it can't just borrow stuff. It has to own its data. And that little move keyword, that's your magic wand for making that ownership transfer happen. Puzzle solved.
Okay, our last puzzle for the day, the trait mismatch. This one is all about traits and promises. A trait can define a method that makes a very specific promise about lifetimes, but then when we go to implement that trait, we might accidentally break that promise. You can think of it like a legal contract dispute with the compiler.
So let's examine the contract. This extractor trait clearly states that its extract method will return a reference that lives just as long as self does. But look at the bad code on the left. It's breaking the deal. It creates a brand new temporary string inside the method and then tries to return a reference to that. Well, that temporary string gets destroyed the second the method ends. Contract violated. The fix, on the right, does things properly. It fulfills the contract by returning a slice that borrows directly from data that's already part of self.
You gotta remember, that trait's signature is a binding contract. If it says you're returning a reference that's tied to the life of self, then you have to return a reference to something that is part of self. Period. Anything else is a breach of contract, and you can bet our grumpy guardian is going to be the first one to call you out on it.
All right, we've worked through our 3 big puzzles. So now let's take everything we've learned and boil it down into a simple, practical toolkit that you can pull out anytime you see one of these lifetime errors pop up.
This right here, this is your new best friend. It's a cheat sheet for debugging lifetimes. Let's run through it real quick. Problem 1, you're returning a reference to something local inside a function. The fix, either return an own value instead of a reference, or borrow from an input. Use this when the data just won't live long enough. Problem 2, a closure is trying to use data that's about to disappear. The fix is super easy. Just use the move keyword. Let the closure own the data. Do this anytime the closure has to outlive its birthplace. And problem 3, breaking a trait's lifetime promise. The fix, fulfill the contract. Just borrow from self. Seriously, this table will solve like 90% of the lifetime errors you're going to run into. So, after going through all of this, I really hope you can start to see the borrow checker differently. It's not your enemy, it's not trying to make your life hard, it's more like a super diligent partner, a tireless assistant who's just trying to help you write safer, better code by catching problems before they can do any real damage.
And to really make that partnership click, try to keep these 2 mental models in your head. First, every time you see a reference, just picture it as a dependency arrow. The borrower depends on the owner, so the owner has to live at least as long as the borrower. And second, whenever you're writing a closure that needs to stick around, think of it as an owner, not a borrower. It needs to own its data.
Once you have this down, you can really start building bigger things with confidence. You can combine all those cool trades and abstractions we've talked about with code that you know is memory safe. This is what lets you start plugging different modules together and building truly complex applications without fear.
And that's a wrap. This explainer was brought to you by Forge College. If you want to go even deeper on Rust, Solana, or pretty much any other Web3 topic, come check us out at forge.college. Thanks for tuning in.